Okay, I would like to explain problem F. A growing tree. We have a tree of a single vertex. We have two operations. Add a child to some vertex and add x to a vertex and its subtree. We want to find the numerical value of all vertices in the final tree. Yeah. Let's consider first of all an easy but very slow solution. Let's do what is said in the statement. So for each vertex, let's store the set of, or an array if you want, of all its children. Yeah? So the first operation, which is add to v, and you add to v vertex as z plus 1. You just need to maintain as z, which is like easier. And you say that adjacency list of v, you need to push back new vertex. So this is the first operation. Sadly, the second operation is slow. Yeah, because in this you need to add to v this value x, but also you need some sort of DFS to traverse the subtree of v and to add x to each of its children, and each of its direct children and indirect children, which is called ancestors. No, not ancestors. Successors, I think. You need DFS. So the first operation will be an O of n on O of one time, but the second operation will be an O of subtree operations, which is O of n time. This is slow. Okay? So this is bad, non-optimal approach. Okay, the second way, which is called postponed operations. So the first operation is the same. The second operation, you just say that AV, sorry, it should be plus equals x. You just say AV plus equals x, and you do not do anything else. What does it mean? It means that actually, not only do you add x to v, but it is also like a promise to add x to all its successors later. So you say number in any vertex means that all its subtree should be increased by this number. For example, this configuration means that actually I have 5 here, and I also need to add 5 to all its children, and direct and indirect. So here it should be 3. And to this 4, I will need to add 5 here and minus 2 here. So in the end, it is 7. And this is 6. So what I mean is this tree, but I store this as this tree because it can be updated faster. Actually, in the end, I can find all these numbers with a simple DFS. Actually, this would work, except I cannot add a vertex. So assume that you add some new vertex. You want to add a vertex with 0, but you cannot, because if you want to add a vertex with 0, here it wouldn't be 0. Yeah, here it would be I guess minus 7. So what I would like to do is find the real value of this vertex and put here minus this value. And this would be possible, but unfortunately this value is sum of all these numbers. and there can be linear number of such numbers. So still, there is a third thing. So actually here, what we need to do is O of n function, which calculates the number in a vertex. This is still slow. Okay? If we could find a number in a vertex, this would be nice, but we cannot. So I came up with the following approach. Let's consider the thing which is called Euler tour. Euler tour. This is a way to make an array of a tree. How do you do it? You make a DFS, and in this DFS, you put everything you visit in an array. So if you let's write some code. So we have vector tour. So here you say the tour dot pushback v. Then you iterate over all to from adjacency list of v, and you say DFS of 2. So first of all, you put a vertex, and then you put DFSs of its children. Actually, what it will result in is after each vertex, you have its subtree traversed in some order. This is nice because actually you now get that each subtree is a segment in some array starting with its root. Now, if you want to add x to some subtree, you just need to add x to some subarray of an array. And this is kind of easy. It's kind of easy because for example, you can do it with a segment tree. So let's make an Euler tour, make a segment tree of it. Let's see what we have in our operations. So the second operation is to add to subtree of v. Instead of that, we take the segment from L v to RV, yeah, where L and R is the positions of the beginning and the ending of this segment. And we add the same value x to this segment. Okay? So this is operation add. And what about the first operation? The first operation is add a vertex. This is the sad part. You cannot easily add a vertex in a segment tree. This would mean that you need some sort of Cartesian tree, which we do not like. Cartesian tree is a nasty structure. Instead of that, we don't do it. What we would like to do is to already have this vertex, but deactivate it. So actually the first part of this problem is to construct the full tree without the second type operations. You just make all the whole tree with zeros. And you fill it with zeros. Okay? Then, if you add this thing, you also sometimes add to some vertices which still do not exist. But let's assume that it's right. For example, you have some vertex, activated vertices. And for example, it has two deactivated children because they're still not in the tree. Well, if you add 2 to this subtree, you also add 2 to here and 2 to here. Yeah, they will be added. It's fine. Then this operation simply says activate some vertex. And during the activation, we need to nullify this number. Yeah, so if it was like 5, it should become 0 now. So we need the following operations. Add on a segment, find element, and add to element. Yeah, for example, if it is 5, then we need to find this 5 and add -5 to this number. Okay? This can be done with a pretty standard segment tree. Nothing really hard here. Or is it? Let me think for a moment. Yeah, it's kind of fast. To do it, you would like to consider the difference array and make the operations on it. What happens here? So add to element just reduced to add segment, yeah? Because you can add to a segment consisting of one element. So you just need to add to segment and to find element. In difference array, if you add x to some subarray, it means -x to this element of difference array and +x to this element of difference array. So instead of that, you need add to element. Okay, what about this one? Find element. To find the element, you just need to sum up all elements of difference array from 0th to i-1st. So sum on prefix. This is what you need. Or sum or segment. I don't care. And this can be done even with a Fenwick tree. You just don't need segment tree, you will need only a Fenwick tree. So you do it, and you get your answer. During the contest, I implemented it by I also reversed all operations, so I went from later to earlier operations. And for me, this operation add to element seemed like this. Gain the answer and store it in an array. After that, it's like same. So I guess that's it. Everything is explained. Also, of course, I failed to get OK from the first attempt because it's ints here. Yeah, but if you add a lot of them, they will overflow the int. You will need long actually for this problem. And long will be enough. Okay, so thank you.